In the first part, we'll look at character frequencies and how to exploit the fact that E is much more frequent in natural language than some other letters, and other scripts will have similar properties. Before, as a prerequisite to that, we'll talk a bit about character encodings. So in the simplest form, an encoding is a function that maps our input alphabet, the source alphabet, to, well, somehow the coded alphabet, but we can't just do letter by letter, because the source alphabet could be, say, the English Latin alphabet with 26 letters, or maybe lowercase, uppercase, many more. And the coded alphabet, often we want, in this case, binary. So we need to do one character to a whole string of characters in the general case. Then we call what we get if we apply this encoding function to a letter, we call that the code word for that letter. Okay, so think about that as bits. Then we can have different codes. The simplest one are fixed length. Every character in the source alphabet is mapped to the same number of bits in the, or the same number of characters in the coded alphabet. But that's not necessarily needed. We can also have encodings that give different lengths. A simple, well-known fixed length code is the ASCII character, the ASCII character encoding, which is listed here. So you see there's not all special letters, no emoji and all that. It's from 1963. It actually specifies 7-bit for each character. It's often used as 8 bits, where the extra bit is either not used at all or used for extended ASCII, where there was this terrible time where you always had to tell your text editor, oh, this file is so-and-so encoded, and then Windows had their own, and Mac had their own, and everyone had their own. Not very convenient, and luckily no longer such a big deal, because most people use something else. But it's a fixed length code. Every character has exactly the same number of bits. And that's all I want to say about these. They're boring. So they're as fast and as easy as it gets, but they do almost nothing in terms of compression, and they're very inflexible. If you invent a new emoji, you're out of luck. So let's briefly touch on the other alternative if we have variable length code words. And that's also an old idea. I guess people know Morse code. What you may not realize is there's not just one Morse code. Again, people had different codings. The idea of having to tell the other party what code you use much predates computers. Here's the international Morse code. That's how Wikipedia shows it, at least. And that shows something that in the ASCII table was there, but not very interesting. You often need different representations are convenient for encoding and for decoding. So here for encoding, you just have an alphabetic list of all the characters, and it tells you the code word, this pattern of dot and dash, long and short, you know. For decoding, that's quite inconvenient. If I tell you dot, 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 what character is that? You have to look at its SOS, right? So starting from that, so you kind of know it's S, but finding that in this table is computationally annoying. That's a technical term. I don't know. Much more convenient is a trie representation of the same thing, where you can say, okay, this is dash or dot. I went dot, dot, dot. Here's the S. Okay. I don't want to discuss Morse code in too much detail. It's just a nice historic example. I want to point out one thing. How many characters are there in the coded alphabet for the Morse code? And the question has two purposes. One is hammer down these the notation for our alphabets. There's also a second part. So let me go back to that representation. Let's aim for 40 people. Okay, nobody voted for zero character for one letter. I guess the one letter alphabet you can pretty much ignore. It's not much you can do with that. Six more. It's quite a variety of answers. I'm looking forward to this. Okay, three more. Two more. One more. All right, there we go. We have answers for most numbers, right? Now, I think the correct answer here is quite clear. If it was only two, so there's dot and dash, obviously these two, but then that wouldn't be enough to unambiguously send something. You also have the gap. So in Morse code, you send letter by letter through the sequence of dots and dashes, but then you have to know when one character ends. And because we talked about tries last week's, you should be familiar with reading tries. What I did here was I put the letters that these correspond to in the internal nodes. That's a clear signal that there's something dangerous going on. If I just see one dot, how do I know whether that's an E or the beginning of an A or one of these others? So I really need this third character that tells me stop right here. Okay. So Morse code is a bit weird in the computer world, but it was not a problem in the acoustic version. Now, what do files most of the time use, text files these days? Unicode encoding or specifically UTF-8 character encoding? And I don't know how many of you wondered how that works. Here's how it works. I guess that's the last bit we can do today. So let me go over this very quickly. The 8 stands for normally use 8 bits, but there's way more characters than 256, so that cannot possibly be the only thing you can do. So what happens is there's characters that are encoded with a single byte. These are the ASCII characters. But then for others, you need 2, 3, or 4 bytes, and there's a special symbol, a special start of the byte that tells you which version you have. And so characters have variable lengths. Some take 1 byte, some take up to 4. Now that's all fine, but think about what that means for jumping to the so-and-so character in a text. You can no longer do that because you don't know how many characters you skipped if they have variable length. And so most things that deal with Unicode, they define code points or bytes as the unit of things to jump over instead of actual characters. It's quite tricky if you think about it to work with these types of strings. But that's what the world has settled for because we care about the space. It's all about reducing the space, why you need UTF-8 most of the time.